Welcome to Florida RV Trade Association Distance Learning Network. And this is one of our advanced classes. And we have one of our vendors, WFCO, with us today and introduce you to Derek. And Derek's going to take us through training on converters, inverters, and transfer switches. So, Derek, you're on. It's up to you now.
Thank you. Hi, my name is Derek Dombrowski. I'm with WFCO, and I'm here to show you some troubleshooting for WFCO products. And today we have a power center, Dec Mount Converter, inverter, and transfer switch. And on each of these products, we're going to show you how to test and troubleshoot. First product we're going to talk about today is our 8955 PEC. It's our most common power center that's out on the market that you're probably going to see in 80 to 90% of the RVs out there. If you flip the door down on your power center, and if you look right here on the product label, at the top of the label, you're going to see model number WF8955. The first two numbers are the series, so it's an 8900 series. The last two numbers, the 55, is the amperage model, so 8900 series, 55 amp DC output model. The first thing we're going to talk about are our converters. So what you need to know about a converter is a converter's primary function is to convert 120 volt AC power into 12 volt DC power. Your 12 volt DC power is going to be operating all your 12 volt items in your coach while charging the battery simultaneously. One thing you need to know is that the coach comes primary before the battery itself. So if you're using 30 amps in your coach and you're using a 55 amp converter, you're only going to have 25 amps available for the battery. So the battery just gets the leftovers of whatever your amperage model converter is. WFCO converters are all 3-stage chargers. So you have a 13.2 volt float mode, you have a 13.6 absorption mode, and you have a 14.4 bulk fast charge mode. These modes are only relevant when it comes to using a battery. And one thing when it comes to battery is batteries are not required for the converter to work, but it will also charge a battery, but the converter will work the same without the battery itself. Okay, so now we have identified the product that we are using, and now we're going to take the door assembly off to get into the guts of the power center itself. And that's going to be 2 screws at the top of the panel that relieve this door assembly to get to the internals. So 2 Phillips head screws take this door assembly off, and now we can get to our AC side and then our DC side. First thing when troubleshooting or testing a converter, never assume the power is on or off. And that's when you're going to want to get to your trusty voltmeter. I'm using a Fluke auto meter, so all I have to turn it to is AC or DC volts, and it measures for me. So depending on the meter that you're using, you want to set the meter is close to the voltage that you're testing. So if you're testing AC voltage, you want to turn it to AC volts closest to 120 volts, so most likely it's going to be 200 volts. If you're testing DC volts, you're going to set it to 20, which is probably going to be as close as you can to the 12 volt range. Let's see if we can set this up. So when testing your converter, you always want to test your incoming power source first. So I'm going to turn my meter to AC volts. And then I'm going to test my power source coming in. So meter is reading 117 volts. And for our WFCO products, the range is between 105 AC volts to 130 AC volts. That's your operating range. Anything below or above, you may be subject to damaging the converter or the internal parts themselves. So we have verified that we have good AC power, so I'm going to plug in our converter. My breaker is off right now, so assuming this is not hot, I would test the AC Busbar that's in the panel itself. It's this metal bar right here with all the stabs where the breakers are actually located onto. So to ensure that I don't have voltage coming through, I'm going to test from the Busbar to my neutral bar, and I should have nothing, which I have 0.1, so that's good. I'm going to check from neutral, and I'm going to check to ground. Also nothing. So we know we have power coming in, and my breaker's off, and my breaker's working properly. So I'm going to go ahead and flip our breaker on. I'm not sure if you could hear that, but the fan has actually spun up for about 2 seconds. That's normal, and it turns right back off. What that is doing is loading up the capacitors in the circuit, so as soon as those capacitors load up, that fan shuts off. So that's normal that the fan came on for a second. So now what we're going to do is check our AC voltage from our main breaker to our neutral bar, and still nothing. So and why is it not getting? I can't get in there. It's hard to do it upside down. Am I getting a reading now? Okay, now I'm getting a reading. All right, so I'm getting 117 volts at my main breaker. Want to make sure we're getting that at the converter as well. And 117 at my main breaker. And when you're checking your voltage, you want to check from AC hot. So AC hot is going to be your main breaker, to the neutral bar, which is the white wires. And you're also going to want to check hot to ground, which is your green wires. Should have around the same voltage, which I actually have a little bit higher on my ground bar, which that's fine. But if you're getting a low reading on your AC hot to ground, that could indicate a bad ground. So you always want to check AC hot to AC ground, because if you're losing a ground, that can actually affect some of your products or the converter as well. Once you have verified you have good AC voltage coming in, we're going to go to the DC side of the converter itself over here, which is our fuse board. As you can see right here, we have our neutral coming in, and right below is our AC hot, so the red and white wire. So you're going to turn your meter to DC volts. And you're going to check between the red wire, which is your hot, and the white, which is your negative. And the converter is reading 13.7 volts. That is what you want to see the converter putting out, is anywhere in between 13.2 volts and 14.4 volts, depending on if you have a battery and what mode it's in. So 13.7 volts is a good volt reading that we're actually reading. Right below those two, we have two 40-amp fuses. Those are your reverse polarity fuses. In order for any of these circuits over here to work, which are going to be your lights, your water pump, your slide outs, any of your 12-volt items, for those to work, these two fuses need to be good. If I were to check my voltage between my positive at the bottom and my negative at the top, right now I'm getting 13.7 volts. That's what would be wired up to your battery at these 2 points, and that's also what would be powering these circuits over here on the right-hand side. If I was to pull these two fuses and now check that same spot, you'll see I have no voltage. What that is indicating, say those fuses are blown. So if those fuses were blown, you'd actually be getting nothing at your battery cables and nothing at your DC fuses. But you measure back at the converter input, and your converter is still working. So if you're reading good voltage at your converter coming in, but nothing coming out to your battery or your 12 volt appliances, you need to check those two 40 amp fuses that I just pulled out. To check your fuses, on my meter I have a continuity check, which looks like a sideways Wi-Fi symbol, but you can also ohm it out. You want to set it to 2000 ohms, and a good fuse should read out about 0 ohms. I'm going to turn my meter to continuity. Again, that's a sideways Wi-Fi symbol, and I'm just going to go across both blades of the fuse. I'm not sure if you can see this, but on continuity on my meter, you'll get an audible buzzing, and it should be reading 0 as well. So 0 is indicating a good fuse. So I'm going to go ahead and insert those two 40 amp fuses back into the power center again. And then with my voltmeter, I'm going to turn it back to DC volts. And then back at my battery connections, which is the positive on the bottom and the negative at the top, I'm getting proper voltage of 13.7 again. 13.7 is what we want. One thing I will show you is on the fuses, there's no fuses in here, so that could indicate a blown fuse as well. If you go from the negative to your positive, which would be your fuses, on the left-hand side you're getting 13.7, so that's proper, even though there's no fuses in it. If you go to the right-hand side, you're getting 13, almost even. The reason there's voltage on both sides of these fuses, even though there's no fuse in there, is that when there is a blown fuse or an open circuit, you're going to get a red LED that's indicating a blown fuse. So that voltage on the right-hand side is normal, and that's what's going to power that red LED for when that fuse does blow. So it's voltage and no amperage, but it is okay to have voltage on both sides of the fuse. Now to remove the main board, you're going to need to start on your AC side, and you're going to start on your converter breaker, which is our 20 amp breaker down here. And to get to this screw to unwire the converter itself, it's either a number 2 square drive or a flathead screwdriver. I'm using a flathead. So the first thing you're going to do is loosen up your screw to your breaker. Release your hot wire. I'm going to take my number 2 square drive and go into my ground bar, which is coming from the converter bottom down here. You can see the green wire coming from the main board down here. So that's the one I'm going to take off the ground bar. And then we're going to go to our neutral bar. Again, your white wire coming from your main board down here is the one you're going to want to take off the neutral bar. So I have my converter AC wires undone. I'm going to go ahead and run them through the holes so I can get it to the bottom. Now we're going to go over to the DC side, and we're going to take off your DC connections. So we're going to go ahead and take a number 3 Phillips head screwdriver and take away your positive and negative that the converter are coming into. Go ahead and loosen those up. You'll notice on the fuse board at the top here, if you can get in there, see if we can get at the top of our fuse board here. It's just, oh, there we go. Yep, that's good. You got 2 little tabs that are holding the top of the fuse board in, right here and over here. Then if you go to the bottom, down here at the bottom of the fuse board, got a little push tab. That's the part you need to go and push down to take this fuse board out. So push that down, slide your fuse board out from the bottom to the top. Now you can take away your positive and negative wire that we just loosened. You're going to use that fuse board again. You're going to run your DC positive and negative out the bottom. Now last thing you need to do is take a Phillips head screwdriver, and there's 2 screws that are holding in your main board. Once you remove those, your main board is now free. This is the only part you would need to replace if your converter was not working or if you had any issues with your 12-volt system. Everything else, the panel, AC side, and the DC fuse board are both going to be fine. One thing you'll notice when you take your main board out, we have a DC fan right here that's on the main board itself. Let's see it. There we go. One difference between our product and some of the other products out there is our fan is not temperature based. So for this fan to run, our fans are load based. So the load being your 12-volt lights, your water pump, furnace, any of your 12-volt loads. After a certain load, this fan will start running. It's not going to start running just because it's hot. So if your fan's running, that means either your battery's charging or you have some lights on. That's going to make that fan run, and it will run continuously until you get that load below the threshold for it to run. The main board comes as it is, so if you get a new main board, you are going to get the fan, heat sink. It's going to come with all your wires, so it's just an easy swap. This is just a regular main board. When you replace this main board, we do have a lithium option. You can replace the same main board that's going to look exactly like this as it comes right now with a lithium ready main board, which the difference between a regular main board and a lithium main board is just the voltage that is there to charge a lithium battery. This main board will still charge a lithium battery to about 80–85%, but if you're going to spend the money for a lithium battery, you might want to replace your main board to a lithium main board that we do have ready. And so we are replacing a bad main board, and now it is a good main board. So the process to put the main board in is just like you had just taken it out. You're going to run your AC wires through the AC side of your panel, and your DC wires through your DC side of your panel. Once you slide your main board in, make sure your wires aren't binding up like mine are. So DC side's on the DC side, AC side on the AC side. So we're going to start backwards from where we took it out. We're going to start by putting in your DC fuse board first. I find it easier to wire up the fuse board first before you put it in. So we're going to loosen your negative and positive terminals. Put your negative wire in the fuse board. You're going to go ahead and tighten it down. And there is a torque spec for proper torque on all of the connections on our panels. And if you look at the back of our door assembly that we had taken off to get to the main board, right down here at the bottom, we got all of our torque specs and a wiring diagram. All of our power centers have a wiring diagram and torque specs for your AC and DC connections. So when you're putting in a new main board or rewiring your AC side, there are torque specs to go by. So we got our negative in. ahead and put our positive wire back in. There, we got that. And again, backwards, we're gonna start by putting in the top first. So it's wedged up into the top, and then that little spot that we pushed down earlier to get it out, we're just gonna push it until you hear a nice little click. So now it's locked in there. So our DC side's wired up. Now we can go to our AC side. We go back to the number 2 square bit to put in our ground wire. Ground wire's in. Now we're going to go to our neutral. Neutral's in. And then we're going to put our converter hot back into its 20 amp breaker. In just a second. I can't see this. All right, so it's nice and secure. All right. We're going to go ahead and plug back into our shore power, or my power source over here. Turn the power back on. We're going to make sure we're on AC volts. Again, you're going to check your incoming power. So main breaker to the neutral bar should be at 117 volts. And main to ground. So hot to neutral, hot to ground. So we got good power coming in. Now we're going to check our converter breaker. Same. So hot to neutral got 117. Hot to ground got 118. So we're good there. So we got good power coming in. We'll turn it to DC volts. And then we're going to check the converter incoming to the fuse board. So positive to negative, 13.7. And then we're going to make sure that all of our circuits and batteries are going to get the same voltage. So positive to negative, 13.7. So we have a good working replace main board assembly. So that's it for our main board. I'm going to turn this off. Switch over. What we have here is a Dec Mount Converter. It's essentially the same thing. It's a converter, 3-stage charger, load-based fan. The only difference is this is a standalone Dec Mount Converter. So it doesn't hold breakers, doesn't hold fuses for your 12-volt side. So to ensure that this is working properly, you're going to, again, turn it to AC volts. You're going to check your power source. So we got 117 volts on the meter. And we're going to go and plug into our power source. Again, just like the power center that we just dealt with, the fan came on for about 2 seconds and then shut right back off. That's completely normal. So we're going to turn our voltmeter to DC volts. So we're testing the output of our 9855 Dec Mount Converter, and you're going to check at your negative and your positive, so your red and black terminals, and you should be getting about 13.6, 13.7, which we are. So we have good voltage there. As you'll notice, next to the positive and negative terminals, you got 2 fuses here, just like we had mentioned in your 8955 PEC. In order for this converter to put out your proper 13.6, 13.7 voltage, these fuses have to be in place or not blown. If these fuses are blown, you'll get no output like it's showing right now. So if your converter is not producing your 13.6, always check these fuses before you replace. If these fuses are good and you're still putting out no volts and you have good incoming AC voltage, you need to replace your Dec Mount Converter, which is essentially just a metal box and a power cord. Just like on the main board we had replaced, our 9855 Dec Mount Converter does have a lithium option. It'd be a 9850. The 50 is indicating that it's a 50 amp. This is a 55 amp model. Our lithium converters only come in 50 amp models. That's including our main boards. So our main board and Dec Mount converters do have a lithium option as a replacement, but they go only to 50 amps instead of the 55. So here we have our 1000 watt inverter. This is our 5110R. Again, this is 1000 watts, which turns out to about 8.3 usable amps. This model right here, the R has a black face, as you can see right here. We do have some models out in the field that you will see, and it probably has a red face. They are still 5110s, but it's going to be the 5110H or 5110HP. There are some differences when it comes to these inverters, and that being is on the back hand side. This is your input coming from your battery. So what an inverter does is take your battery power right here and turns it to 110 volt AC power. So it takes 12 volt, turns it into 110 volt. So these are your inputs. The R stands for reverse polarity. So if you were to hook up your positive and negative backwards into the 5110R, the unit will just not work. If you were to hook up these connections backwards in your H or HP 5110, that unit will be rendered useless and you would have to get a new unit. So don't hook it up backwards. Again, 1000 watt inverter, our 1000 watt inverter is a pure sine wave inverter, so this is safe for small electronics, cameras, computers, anything that needs a clean signal source. So again, 1000 watt pure sine wave inverter. What we're going to do is simulate a battery connection to the inverter. So we're going to use a converter to get our 12 volt power source. So we take our positive and put it to our positive terminal, and our terminals are labeled positive and negative. So don't just go by the color. You want to go by positive wire to positive terminal. But again, if you hook it up backwards on the R, it's just not going to work, and as soon as you correct the polarity, it'll be just fine. So hook up our positive and negative. So that's our 12 volt coming in. That's what we need for the inverter to work. You need a positive 12 volt source to operate your inverter. Next, what you're going to do is there's a little thumb screw right here. Loosen that up. You're going to take this little door off, and you're going to find a black, a white, and a green wire. So your hot, your neutral, and your ground wire. This is your 110 output wires. So when you have your 12 volt coming in, your inverter is going to take 12 volt, turn it into 110 volts coming out of these 3 wires. You'll notice there's also a plug-in cord that comes with this inverter. This plug-in cord is for pass-through power. So when you're plugged into shore power, this plug's going to be plugged into a receptacle, and whatever power source you're plugged into, if this is plugged into a receptacle, it's going to pass through the inverter and come out these wires themselves also. Your shore power is going to be primary, so even though you have a battery hooked up, once you plug into shore power, relay inside is going to make it pass through the voltage that you're plugged into and not using your battery voltage. So once we take the sleeves off of those, now we have some bare wire to 110 power. So we want to make sure these wires don't touch. And you always want to remove your load when you're testing your inverter, because if you have a wiring problem, you need to get to the inverter wires themselves, not just the reefer wires or whatever this may be hooked up to. You always want to check the wires coming out of the inverter. So we got our battery connections. We're not going to plug into shore power for our pass-through. And we're going to plug in our 12-volt power source, or our battery. So now we have battery voltage. I'm going to spin this around so you can see the front right there. Okay. So the inverter's in off position. It's a two-piece button, so in is on, out is off. So once you turn this on, you're going to see that screen light up right here. After a second, you're going to get a yellow or amber light. That is indicating that you are inverting. So you are technically using your battery, creating 110 volts coming out the backside. If we can zoom in on the screen a little bit, you're going to see, hard to see, but you see it says 116, and next to the 116 it says ACV, so AC volts, 116 AC volts. There's a button right here next to the screen. It's hard to see, but if I push that button one time, it's going to switch the screen, and it's going to say 0.03, and it says amps at the bottom of the screen down here. So it's telling you how many amps are being drawn off your inverter. If you hit that button one more time, I can't see. Okay, there we are, 13.3. One more time, and now we got 13.3. That's telling us our VDC coming in, so it's telling your battery voltage. So you have a button that has 3 different modes. Your first mode is going to be AC voltage coming out of the inverter, what the inverter's producing. Your second one's going to be AC amps that's being drawn off of the inverter, and the last one's going to tell your battery voltage. So our battery voltage right now coming into the inverter is 13.3 volts. So we're back to AC volts. That's what's going to be on the very first time you turn on the inverter, is your 116 AC volts. That's what it's putting out. Just because the screen says it's putting out 116 AC volts, you want to check at the wires coming out the back of the inverter that I had show you, your black, white, and green wire. So your black's going to be your hot, white's going to be your negative. So make sure you're on AC volts. You measure from your black and white wire coming out the back, and see what kind of reading we're getting. 115 volts coming out. So the inverter screen says 116, our voltmeter says 115, so we're about a volt off, which is pretty good. So we got the voltage coming out outside the wires. So you're also going to try get a better connection. Yep, so 115 volts. Now if we were to turn this inverter off, we're going to take this power cord and we're going to plug it into the power source also. Alright, so we just plugged our cord in that I told you is for pass-through. Now on the inverter we have a green light. Green light is indicating AC pass-through, so that means you're plugged into an AC power source and the inverter's just passing through what it's being given. You can turn the inverter on and you're going to get your screen readout telling you the voltage that it's passing through, and it's probably going to be a little bit higher than what we were just producing. just because that's your shore power coming in. So 120 AC volts is what it's reading out now, and that's on your shore power. This little button that we just used a second ago will not work on shore power. So when that light's green, all it's going to tell you is what it's passing through, is because the inverter's not technically doing anything other than passing through the voltage. Even if you turn this button off and you're on pass-through, that green light's on, you're still going to have hot voltage coming out the back of this inverter. So if you measure between your black and white wire again out the back, which is your output, we're getting 118 volts. So just because your button's not in the on position, if you have a green light on, these wires are still hot. One thing you will notice is when you turn this button on, you probably can't hear it in this video, but these fans are running. On WFCO inverters, when it's on, the fans are on. It's not heat based, it's not load based. When it's on, fans are on, and they'll stay on until you turn this button off. The fan goes off. We'll go ahead and unplug our pass-through. I'm going to go ahead and disconnect our battery, so we have no voltage coming to the inverter itself. I'll just ensure that I don't have any voltage coming out of my wires out the back, which I have nothing. And if we spin this inverter around, you'll notice right here there is a little rocker resettable AC circuit outbreak, or AC breaker, not outbreak, excuse my language. It is resettable, it's not an auto reset, so this is going to trip if you exceed the amperage of the inverter, or if the inverter is miswired. This breaker will trip, so if you are not getting output at these wires coming out the back of the inverter right here, always check this breaker. You cannot manually trip this breaker, so I could sit here and push on it. It won't trip the breaker, so you can't test the breaker. But you'll notice when this breaker trips, you'll see a little white edge to it. And as long as you reset it, you'll get your output back at the wires themselves. And that's all we got for an inverter. Now we're going to talk about WFCO's transfer switch. This is our T30 transfer switch. And a transfer switch is essentially just a time delay for your generator to do its self-diagnostics before it passes on to the panel and coach itself. So first thing we want to do is remove the screw from the top of your T30. This is going to give you access to your wires. And if we can zoom in on here, there we go. It's going to be labeled. So you have a label right here that's indicating your shore power. This one's going to be indicating to your distribution panel. And these are your generator wires over here. Oh, these are your generator wires over here. In a transfer switch, your generator leg is going to be primary. So when you start up the generator, the relay inside is going to switch over and pass through your generator wires. So first thing we want to do, we're going to test the shore. So we got a black and white wire for your shore leg. We're going to mock our shore power by putting our hot shore leg, our neutral, and then down here at the bottom, you got a ground bar, so your ground's going to go down here. So right now we are wired into our shore panel, or our shore leg. So as soon as we plug into a good 110 AC source, you're going to get your 110 out of your panel wires right here. So you're going to turn your voltmeter to AC volts. You're going to test your power source. And right now we got 118 volts. And again, just like our converters, 105 AC volts to 130 AC volts is the proper voltage needed for our products to work. So we are good. So we're gonna mock our shore power by plugging in our shore power cord. There is no time delay, so if we stay on our AC volts and measure at our panel output wires, we are getting our shore power through our panel wires. That would be going to your power center or your breakers that is being into your power center. So we're gonna turn our shore power off. We're gonna switch over to our generator leg. So I'm gonna keep my ground in the ground bar. I'm gonna go to our generator leg. All right, we are now wired into our generator leg inside the panel itself. All right, we're gonna mock and test our incoming generator voltage. Again, we have 118 volts. And then now we're gonna we're gonna turn our generator on by plugging in. And you'll notice if I were to put up my panel wires, we're getting nothing. It takes about 30 seconds. After 30 seconds, we're gonna have to wait. You're gonna hear an audible click. So give her the 30 seconds. We just heard an audible click. Now you're gonna go back to your panel wires. If I can get there we go. Once you get your meter on there right, you got your 118 volts coming out from your generator. So that 30-second time delay is the whole purpose of a transfer switch, and that gives the generator 30 seconds to do its self-diagnostic, so it's not putting out high or low voltage and damaging your AC appliances in the coach itself. So turn our generator off. Go ahead and tuck our wires back in.
And Derek, before you put that all back together, I was noticing some new type of connectors you have on the end of your wires there.
Thank you for bringing that up. These are actually WFCO connectors. Not sure if we can get a zoom in on these. I'll take one off. These are WFCO connectors. WFCO is a brand, and WFCO is probably the only one that is certified through the RV industry. There are some Chinese knockoffs, but WFCOs themselves are being used throughout the OEMs in our industry, getting away from bell connectors and little lock nuts. We are actually going to be using the standard in our transfer switches and on our power centers. It's going to be an option. It's not going to be on every power center, but on our DC fuse boards, we're going to have WFCO connectors like this, so you're going to get away from the screw terminals. And what these do is, you take your, where am I at? There we go. So you got your stranded wire or solid wire, doesn't matter. And all you do is have to put it in to the WFCO connector itself and snap it down. Once you got it locked down. I mean, these things are almost nearly impossible to pull out. It makes a good solid connection. And you won't be able to see it, but on the back side there is a little opening that if you had your hot, your black wire, and your negative hooked up, you can actually put your voltmeter on the back side. There's an opening where you can test without pulling the wires out, so you're gonna eliminate a lot of wasted time trying to get connections off and putting them back on by just being able to put your prongs on the back of a WFCO to test your voltage between connections. So WFCO is something that we are starting to use on some of our products, and a lot of the OEMs are using as well. All right,
Does that finish you up?
I'm good to go.
All right, that'll finish us up for this session on converters, inverters, and transfer switches. So thank you, Derek, for all that great information. And anytime you have any questions or anything, as usual, be sure and send us your questions, and we'll be glad to answer them. All right, thanks for joining us.
Thank you.